These notes go with section 8.1 in your text, and this is on the topic of relations and functions. First, we need to understand what the word relation means in math. It doesn't mean like a relative, an uncle, an aunt, or something like that. What a relation is simply is a rule that relates an input and an output. Typically, we're going to track relations by tracking what we put in and what we get out. And in math, the things we put in and get out are typically going to be numbers. So an example of a relation might be, we put in a 3, we get out a 4. We put in a 5, we get out a 6. We put in a 7, we get out a 10. Some relations have a very predictable pattern. Some relations don't have predictable patterns. A relation is simply something that relates an input and an output. The domain is the name we give to the numbers we put in to a relationship. So for example, here, the domain would be 3, 5, and 7. Those are the numbers that I put in here. The range is the numbers we get out of a relation. So in this case, the range would be 4, 6, and 10. Input is another word for domain. It's the thing that we put into the function. Typically in math, we're going to track these using the variable x. We're going to use x to be our input. Output is the range, the things that we get out of our relation, and typically we're going to track that using y. Now there's nothing magical about x and y. We use them often by convention, but we could have our inputs be m and our outputs be p. Or if we were working with a specific problem, maybe the input would be the number of cats we have and the output would be the number of kittens they have over long term. So we might use c and k here. The input and output variables can be anything, but very often you'll see x and y used this way. A function is a special kind of a relation where each input has exactly one output. And this matters. So for example, here I have this relation where I put in a 3, I get out a 4. I put in a 5, I get out a 6. I put in a 7, I get out a 10. So far, each input has only one output. Even though there isn't a predictable pattern here, this relation still follows the criteria for being a function. Each input has exactly one output. If the next number I put in is a 9 and I get out a 10, this is still a function. Even though I got the same output twice, I know when I put in a 7, the only thing I get out is a 10. Even though the next number, 9, also spits out a 10, these inputs each have their own output to go with it. It just happens to be that their output is the same. What would make this be not a function is if I were to come along and put another 9 in again, and this time I got an 11 out. This is no longer a function. This makes it not be a function because the next time I come in and put in a 9 to this function, have 9 as my input, what am I going to get out? Am I going to get a 10? Am I going to get an 11? Am I going to get something different? So this would make a relation not be a function. We'll come back to this vertical line test when we start graphing these points in a little bit. But the vertical line test is a graphical way to determine if a relation is a function. If a particular set of input-output pairs meets this criteria, that each input has exactly one output that goes with it. So let's try some of these out in examples. First, let's work with the domain and the range. So here's a particular relation. This is the relationship between the age in years of some spruce trees and their height. So the younger trees are shorter and the older trees are taller, and this makes sense. We would expect this relation to be true. So this relation consists of a bunch of ordered pairs. Here's our first ordered pair, 5, 13. That means that when the age is 5, the height is 13. The next ordered pair is 10, 25. The next ordered pair is 15, 34. Notice that I'm just taking each pair from this table and writing it as an XY pair. The next one is 20, 43. That's this one. And the last one is 25, 52. So those are the ordered pairs in this relation. The domain of the relation is the set of all inputs. In this case, ages. The range is the set of all outputs. In this case, heights. So the domain is the set of numbers that represent the ages. The domain is these numbers up top, 5, 10, 15, 20, and 25. Those are the numbers that we put in. The range is the outputs. It's these numbers here, 13, 25, 34, 43, and 52. So the domain is the set of numbers we put in, and the range is the set of numbers we get out. There's a number of different ways that we can represent a relation. One is we can have a bunch of ordered pairs. When the input is -3, the output is 2. When the input is -2, the output is -2, and on and on. So there's different ways that we can show these. One is we can notice that these x, y pairs can be graphed on a coordinate plane. So we can graph these ordered pairs as points in a coordinate plane. So this first point, -3, 2, we start at the origin and go back 3 and up 2. That's our first point. For the next point, we go back 2 and down 2, so we're here. For the next point, we go right 1 and up 1. For the next point, we go right 1 and up 3. And for the last point, we go right 2 and down 3. So these points, shown here on this coordinate axis, are just another way of showing the ordered pairs that are listed above. Another way we can do this is using something called a mapping diagram. A mapping diagram draws arrows from the inputs to their corresponding outputs. So first, let's make ourselves a list of all the numbers that we're going to put in to our function. We put in, let's see, we put in -3, we put in -2, we put in 1. I don't have to list 1 twice. We put it in twice, but I'm just listing out what are the specific individual numbers we put in. And the last number we put in is a 2. So there's 4 different numbers that we put in. Then I'm going to list the outputs. What are the numbers we get out? Well, we get out a 2, we get out a -2, we get out a 1, a 3, and a -3. There's no duplications in this list, so I don't need to skip anything here. Now we're going to use arrows to connect each input with its output. So let's look at this first ordered pair here. The input of -3 goes with the output of 2, so I draw an arrow that maps this input to its output. The next one, an input of -2, gives me an output of -2. The next one, an input of 1 gives me an output of 1. The next time, an input of 1 gives me an output of 3. Right here, I can tell that this relation is not a function because this input does not have exactly one output. This input, 1, has 2 outputs. I can see from these little arrows that I'm not sure which way I should go when I put in a 1, whether I should go to an output of 1 or an output of 3. The last is when we put in a 2, we get out a negative 3. It's important that we not duplicate numbers in our input list or in our output list, because if I had duplicated this 1 here, I wouldn't notice right away that the input of 1 has 2 separate outputs. I wouldn't see this arrow splitting off. This is called a mapping diagram. Next, we're going to try and identify whether a particular relation is a function. So in this one, it says, let's look at the relation in example 1. So let's flip back to example 1. In this example here, is there ever a case where we put the same number in twice and get different numbers out? It doesn't look like there is, because here there's no time where we put the same input in twice. The input of 5 has exactly one output, it's 13. The input of 10 has exactly one output, 25, etc. So the relation is a function because each input does in fact have exactly one output. This makes sense when we think about it. The input is the age of the tree. And a single tree can have only one height at any given point in time. I can't have a single tree that is 10 feet tall and 20 feet tall at the same time. That doesn't make any sense. So if my input is how old the tree is, that is, how much time has passed, the height, the output, can only be one thing at that point in time. In example 2, then, if we look at this relationship here, this relation is not a function because the input 1 has 2 different outputs. When I put in a 1, I'm not sure whether I'm going to get out a 1 or a 3. So that's not a function. Next, you should pause this presentation while you work through these 2 checkpoint questions here. First, identify the domain and range. So you might write it like this, domain, and then list out the domain of that function, and then range, and list out the range of that function. And then it says, tell whether the relation is a function or not. That's a yes-no question. Is this really a function? Does each input have exactly one output that goes with it? When you're done with that, you can resume this presentation to go on to the vertical line test. The way the vertical line test works is that we take a relation represented as a graph. Remember, before we had a bunch of ordered pairs and we plotted them on a coordinate plane. So we've represented our relation with a bunch of points. We notice that if we draw a vertical line, that's a straight up and down line, through each point in this relation, there is no time where a vertical line crosses 2 points. Each vertical line only crosses 1 point in our relation. This first line only crosses -3, 0. The second line only crosses -2, -3. The third line only crosses 0, 1. The fourth line only crosses 2, -1. And the fifth line only crosses 3, 3. This tells us that the relation represented by the graph is a function. Why does this work? Well, let's look down at example B here. The first line that we would draw through this goes through 2 points, -3, -2, -3, -1. What that means, if I put those 2 points in an XY table, the first point, -3, 2, and the second point, -3, -1, when I put in a -3, when my x coordinate is -3, I'm not sure whether my output, my y coordinate, should be 2 or -1. 2 points that have the same x coordinate are going to lie along the same vertical line. These 2 points both lie along the line x equals -3. If we were to make a mapping diagram for these, our inputs would have only the number -3 for those 2 points, but our outputs, we would have 2 and -1. And our mapping diagram would show we're not sure when we put in a -3 whether we get out a 2 or a -1. So the relation represented by this graph is not a function